In our last video, we began discussing the fine structure, uh, these perturbations to our hydrogen atom energy levels due to various things. The first one we discussed was due to last video was the relativistic correction. When we take into account sort of the kinetic energy of that electron bound to in our hydrogen atom, we realize that there's sort of a significant contribution or relativistic effects. And when we took that into account, we derived what those energy corrections would be. Today, we're going to look at the other contributing factor to the fine structure, and it's what's called the spin-orbit interaction. Um, and what this is essentially is you can classically think, if you think about classic view of an electron orbiting a proton in a hydrogen atom, you have some you can think of it almost like moving around the electron. And what happens is, well, moving charges create currents, or moving charges are currents, and those create magnetic fields. And these charges have angular momentum and magnetic moments. So magnetic moments in those magnetic fields will experience will have their energies affected. Um, so one way to look at this is, well, if I take the view of, I'm this electron and I'm going around in this circular orbit, say, it's a really simplified view, but what I am actually viewing from my frame of reference would be a proton looks like it's going around me like that. And this proton is a moving charge, so we can think of that as being a current going in a loop around me. And that's going to create a magnetic field at the electron. That electron's going to experience that magnetic field. Since it has a magnetic moment, that's going to affect the energy. So what does that look like? Well, the magnetic field from a current going through a loop like that is just equal to mu naught, that current, over twice the radius of that loop, right? And if I'm looking at a single charge going around this circle here, the current is just the charge per time that passes some plane. So that's going to be one electron, one positive fundamental charge, sorry, one proton rather, divided by the period, the time it takes to go once around, right? And that period for something going around in uniform circular motion is just 2 pi r divided by its velocity, right? So putting those together, I end up with a current going around the loop of E times V over 2 pi r, right? Now, we're doing quantum mechanics, so we're doing that. So we typically, rather than thinking about velocities, we think about momenta, and the angular momentum of that particle going around a circle would just be r cross p, is how we define the angular momentum of a particle, which would be mv times r. It would have a magnitude of mvr. So what that means is that velocity of that we're looking at is going to be the angular momentum divided by m times r. So we can plug that into our current going around the loop, and we essentially see that from the point of view of the electron, it sees this current going around the loop with that's equal to E L, the angular momentum, over 2 pi m r squared, right? And we can plug that into our magnetic field, and the magnetic field that electron sees is equal to mu naught over 2r times E L over 2 pi m r squared, right? And we can do one more little trick here. It's just sort of changing units. We know that the from E and M that the speed of light is equal to 1 over mu naught E naught in vacuum. So we can sort of replace that with mu naught is equal to 1 over epsilon naught c squared. And what that all comes out to is, classically, in this sort of simple model we've made up, we have a magnetic field that's equal to E L over 4 pi epsilon mc squared r cubed, where now we've got this written in terms of our old friend, the rest mass, and this 4 pi epsilon naught. And we've got our magnetic field, and now we can start to think about, okay, I'm an electron in this magnetic field. How does this affect my energy? And well, the energy of the interaction of my magnetic moment with that magnetic field is just negative my magnetic moment dotted with the magnetic field I'm in, right? And we know for an electron, the magnetic moment is just negative E over m times that spin operator. That's the magnetic moment due to the intrinsic spin. So plugging that all in, the energy of the interaction due to the spin orbit coupling is just negative E over m, my s, my spin vector, spin angular momentum vector dotted with that magnetic field, which is EL 4 pi epsilon naught mc squared r cubed. Or putting that all together, I have the energy of the interaction as being E squared all divided by 4 pi epsilon naught m squared c squared r cubed, spin operator dotted with that angular momentum. So this is sort of the model we're looking at. We change that spin angular momentum vector and that orbital angular momentum vector into our quantum mechanical operators. And this gives us our Hamiltonian for that spin orbit interaction, and which we'll now treat as a perturbation to our hydrogen atom and see what those energy shifts and how that affects the energy levels in our atom. To figure out to apply perturbation theory to this perturbation Hamiltonian, we're going to need to know what the matrix elements of this Hamiltonian are. And again, we have to be careful here, right? This involves a position part, it's got this r cubed in the denominator here, and the spin part, where it involves the spin of our electron and the angular momentum of our electron, right? So our zeroth order states, when we solve the Hamiltonian, when we solve just the unperturbed hydrogen atom, we're just those NLM states and that. But we have to also include the spin part here. So we have, just like we did with the hyperfine interaction in that, we've got sort of the space part of our ket and our spin part, and we have to consider the full spin space of this system. So it's those quantum numbers that we're concerned with are going to be N, L, S, MS, and ML, right? Where we've got the principal quantum number, the orbital angular momentum quantum number, the spin quantum number, and then the Z components of the spin and orbital angular momenta. Now, this is our uncoupled bases, right? This is the one where we're looking at the Z components of the spin and the Z component of our orbital angular momenta. We know that they're interacting, right? This isn't our system isn't diagonal in that, so we're going to want to switch to the coupled bases. That's going to involve the total angular momentum. We're going to want to switch to coupled. That's going to be the NLS total angular momentum, and then the Z component of that. Sorry, it's written pretty sloppy. The Z component of that total angular momentum, right? And that's the bases that we're going to want to use to look at this. And how do we do that? Well, we do sort of the same thing we did when we were looking at the hyperfine case, right? We define our total angular momentum, J, as just being the addition of our spin and orbital angular momenta. We know that J squared is then just going to be L squared plus S squared plus 2 L dot S, which gives us this L dot S that's in our Hamiltonian is equal to 1/2 J squared minus L squared minus S squared, right? And all of these operators, the L squared, S squared, J squared, are all diagonal in the coupled bases, right? We also saw when we were doing the hyperfine interaction that we could write this in terms of raising and lowering operators if we wanted to, where this was 1/2 L plus S minus plus L minus S plus LZ SZ. So we can write this two ways, but the point is this is diagonal in our coupled bases. So we want to use that basis to figure out what our first order energy correction is. Now, first order perturbation theory essentially just says that first order correction due to that spin orbit is just the matrix elements of the diagonal matrix elements of that perturbation Hamiltonian. So in our in our coupled bases, that looks like this. We have our Hamiltonian, so we can bring out all our constants. That E squared over 8 pi epsilon naught m squared c squared, and we end up with this 1 over r cubed space part, and that L dot S and L S J J and that L dot S term, and this space part we've actually calculated before. I'll just leave it like that, but we have this as our first order energy correction, 1 over r cubed space part, and our I'll just leave it as JMJ L dot S, those matrix elements. This space part we calculated way back. It was one of those integrals we looked at in chapter 8, I believe, when we were looking at the hydrogen atom. That matrix element, or the expectation value for our hydrogen atom, 1 over r cubed operator, is just 1 over a naught cubed n cubed L plus 1/2 L plus 1. So we have that term, we have those constants, we have to figure out these matrix elements. And we remember, we just showed that L dot S can be written as J squared minus L squared minus S squared. And we know the action of all of those operators on our coupled bases, right? We know that J squared acting on that NL SJMJ operator just gives us, H bar squared J plus 1 operating on that same state, NLS JMJ. And similarly, the L squared operator acting on that state gives us H bar squared L plus 1 and LS JMJ. And the S squared operator gives us, a similar eigenvalue equation where it's S plus 1. These are, if you think way back to when we first started discussing just generalized momentum operators, the squared operators, had this eigenvalue equation, which sort of defined what the quantum numbers for those whatever type of angular momentum we were looking at. So if we take these eigenvalue equations, or the action of those operators on these states, to figure out those matrix elements, we see that the NLSJMJ L dot S matrix elements is just going to be equal to H bar squared, and it's going to be J plus 1 minus L plus 1 minus S plus 1. And that's our matrix element. So we can put this all together knowing the spin part of our matrix element, this spatial part and these constants out front, we can figure out that our first order energy correction due to the spin orbit interaction can just be written as, well, E squared, all those constants out front, 8 pi epsilon naught m squared c squared. That space part, which is 1 over a naught cubed n cubed L plus 1 half L plus 1. And then this spin part here, from the spin part here, h bar squared, j plus 1 minus L plus 1 minus s plus 1. I'm missing another bracket in there. So if we take that and think of, with our electron in our hydrogen atom, our S value is 1/2. This whole thing, this term here ends up just being 3/4, and this thing simplifies to this. Right? And that's what we have for our first order interaction, our energy correction. If we think back to sort of our fine structure constant, we had this, alpha was equal to E squared over 4 pi epsilon naught h bar c. And we had A naught, the Bohr radius was just 4 pi epsilon naught h bar squared over m e squared. We can sort of take these and simplify them, and what we find is, we have alpha A naught is equal to h bar over alpha cm. So we can substitute this and this into that sort of constant out front, and this energy correction simplifies to the spin orbit equal to 1/2 alpha to the 4 mc squared times this j plus 1 minus L plus 1 minus 3/4 all over n cubed L plus 1/2 L plus 1. And that gives us our first order energy correction due to this spin orbit interaction. And we see that it is on a scale of alpha to the 4, just like the relativistic correction. So it's on the same order of magnitude, same scale as that. They come together, they're the two corrections of that scale to make the fine structure, or to give us the fine structure in our hydrogen spectra. Now, one thing that's worth noting is if we look at any of those L equals 0 states, so like there are S states in that, this denominator actually goes to 0, and it looks like this energy correction blows up. Turns out when L equals 0, the numerator also goes to 0. If you look at that, we end up with 3/4 minus 3/4. And that kind of saves us. But this sort of makes sense. So, when the angular momentum, orbital angular momentum is 0, there's no, you can't really have this spin orbit interaction. If that angular momentum is 0, if we think all the way back to our classical sort of picture of what this interaction comes from, if there's no orbit going around, we don't see that magnetic field from that orbit, and we don't have that interaction. But anyway, putting the fine structure together, all together in here, we have, this fine structure perturbation that we want to account for in our hydrogen atom, right? And that's just equal to that relativistic correction, the first order relativistic correction we derived last video, and now this spin orbit energy correction that we derived this time. we figured out that the relative correction was negative 1/2 alpha to the 4 mc squared times 1 over n cubed L plus 1/2 minus 3 over 4 n squared. And we just showed that this spin orbit interaction was 1/4 alpha to the 4 mc squared times that j plus 1 minus L plus 1 minus 3/4 all over n cubed L plus 1/2 L plus 1, right? So this is what our fine structure, whoops, sorry about that. Our fine structure energy correction looks like. And this can be simplified a lot. I'm not going to go through the bunch of algebra to get to it, but essentially this boils down to negative 1/2 alpha to the 4 mc squared, um, sorry, mc squared times 1 over n cubed times 1 over j plus 1/2 minus 3 over 4n, right? And that's our fine structure correction that we can include in our hydrogen atom energy spectrum, and we see shifts in all of these energies, not all of them, but in the energy of our states in hydrogen. It lifts some of the degenerate, like I said, there's spin degeneracies in our zeroth order Hamiltonian or zeroth order states of hydrogen. This lifts some of those degeneracies. We're going to continue to discuss this sort of stuff. Next thing we're going to look at is we've looked at these sort of we looked at the hyperfine interaction, which was the sort of magnetic interaction between the nuclear spin and the electron spin angular momenta. We looked at this spin orbit interaction between the spin angular momentum and the orbital angular momentum of the electron and hydrogen. Both of those are sort of internal effects, magnetic field effects. We're going to turn our head to what happens if I apply an external magnetic field to the hydrogen atom, and how does that affect our energy levels. If you have any questions on this, bring them up in the synchronous session or email me, and we will discuss it further. I will see you then.